So, hello everyone, my name is Martin Hedlund. I'm here today to present Rowing Beyond, investigating steering methods for rowing-based locomotion in virtual environments. And I'm presenting this on behalf of Cristian, Bogdan, Gerrit, Meixner and Andrii Matviienko. And this project was a collaboration between KTH Royal Institute of Technology and Heilbronn University of Applied Sciences. So, exergames is a form of games where you use physical activity as input into the systems. And rowing machines could be great for this, as the physical effort you do while you're rowing can be used as input to locomotion in virtual environments. So the speed of the rowing machine can be used as input here to move a virtual character in a virtual environment. And this could be used currently for one-dimensional travel, so that is moving forwards or backwards. But what if 2D and 3D locomotion was available? That could open up whole new game design possibilities, as players could travel and explore freely, and this could offer a more engaging player experiences through mastering of steering controls. So what has been done before? So there are a number of previous research projects on exergames using fitness equipments, for example indoor bikes and treadmills. And the focus of these projects have included demonstrating the feasibility of using this equipment as an input for locomotion, adaptive interfaces and lateral steering. So that is going from side to side, but you're still following a one-dimensional path. In terms of rowing projects, the focus has mainly been on facilitating a proper rowing technique. In terms of commercial applications, we have VS Fit, and in that one you can use indoor bicycles as locomotion input. And then for that one you have lateral steering, so once again moving sideways but following a path. And we also have HoloFit. And for that one, rowing machines are a possibility, actually, but only for one-dimensional movements. But isn't this kind of boring in a way, to be stuck in one dimension? And wouldn't it be nice with steering controls for a rowing-based exergame? But currently, no one has implemented such controls to our knowledge. So research is needed to understand how steering methods can be implemented for rowing. And I will now present how we implemented steering for rowing in VR and what we learned when we evaluated these steering techniques. So, how can we receive input for steering while rowing? So, steering methods in VR locomotion are typically categorized based on which of the user's body parts are involved in generating the input. So, this can be grouped into head, torso, hands, legs, and feet-based interaction techniques. So I will go through the techniques and describe which ones we have implemented. We did not use torso or leg-based techniques. As you can see in the video here, the torso kind of creates a strained movement and the legs needs to be used for pull resistance while pulling. We did implement a head method to start with, and with head-based steering you can use the 3 degrees of freedom position and the 3 degrees of freedom orientation of the VR headset as input sources. But position would mean you were leaning from side to side, and this could cause you to fall off the rowing machine. So therefore we used orientation, and with orientation we mean looking left and right, steers left and right, looking up and down, steers up and down. And the second method we implemented was based on hand-based interaction. And for this, the rower is constrained that the hands must remain on the handlebar. But we can use the input controllers, or we can use an input controller attached to the handlebar as input means. So this means that we can use 3 degrees of freedom of position and orientation of the handlebar as input. But in practice, as you see in these videos, only the Z orientation, or the roll axis of the handlebar, is actually feasible, as the other ones would create very unnatural movements. But since this one is the only one available, how do we do up and down? And for this we use 2 buttons, which on the right hand side you go up if you hold that one, and on the left hand side you go down if you hold that one. And finally, we implemented a feet-based interaction. And for feet-based interaction, we can use 3 parts of the foot. So the toes, the toe joints, and the heels. But the same with legs here. The heels needs to remain on the footrests to generate pull resistance. So we use toes and toe joints. And for this, we used pressure sensors, and the differences between the pressure sensors determine the amount of steering force applied. And the rationale for our up and down implementation is based on how the body tilts when pressing with either toes or toe joints. So as you can see in the video here, pushing with your toe joints make you tilt backwards, i.e. moving up, and the opposite is you press with the toes, you tend to tilt forward, i.e. going down. So how does the virtual environment look? What is the context that we're evaluating this in? So we created a VR environment, and you can see a person here rowing in a 2D scenario, which steers a virtual rowing boat on an ocean. And onto the right here, we see a 3D version of that, in which the user can both move on the ocean, but also fly into the air. So, to understand how the steering methods impacted locomotion, we conducted a user study with 24 participants. And for that one, we asked, how do user performance, VR sickness, and user experience differ between steering methods in 2D and in 3D? And we had 6 conditions for this. So the 3 steering methods which allowed for locomotion in 2D were 3 of the 6 conditions. And then the other 3 were the extension of this method that allowed for locomotion in 3D. So to answer our research questions, we used a coin collection task. Participants had to collect coins by maneuvering the virtual boat as quickly as possible and collect as many coins as possible. And we always spawned 2 coins so participants could estimate a trajectory. We collected the following measurements. For RQ1, i.e. user performance, we collected completion time, travel distance, rowing speed, coin offset, and coin collection rate. For RQ2, we used an SSQ. And for RQ3, we used a NASA TLX to estimate perceived workload. And then we had a bunch of 5-point Likert scale questionnaire to estimate enjoyment, ease and frequency of use, intuitiveness, orientation, fatigue, and exertion. And of course, we also collected qualitative feedback, both so that the participants had the chance to rate which method they liked the most in regards to different aspects, but also that they can provide nuance and comments on what they had experienced. So what are the results of this? So for task completion time, we found that the head method was the fastest, followed by the hand method and then the feet method. For travel distance, we found the opposite, so that participants travel longer distances with the feet compared to hands compared to head. For coin offset, when they missed a target coin, how off were they? And then we can see that they had less coin offset for head than the other methods, and the hands and feet were similar in 2D, but not in 3D. So we can really see feet in 3D here sticking out. For coin collection rate, we saw that heads and head were better than hands and feet. So they collected more coins with the head method. And hands and feet were similar in 2D, but not in 3D. So once again, participants collected less coins with feet in 3D. For the SSQ course, we found no significant difference in VR sickness between the measured scores. However, we did find that participants experienced more sickness in 3D than in the 2D conditions. So for perceived experience differences, we found that participants experienced the workload to be more mentally demanding using the feet method compared to the other methods. And we also found that hands were also perceived as more mentally demanding than head, and that locomotion in 3D was perceived as more mentally demanding than locomotion in 2D with either method. For the Likert squared questionnaires, we found that for intuitiveness, the head method was found to be the most intuitive, and feet in 3D was found to be the least intuitive. For ease of use, we found the same pattern, and for orientation, we found the same pattern. And overall, the 2D method scored better than the 3D methods, with small differences for head and hands and a big difference for feet. On the other hand, for enjoyment, we found no difference between head and hands and the feet 2D methods, but we did find that feet in 3D was the least enjoyed. Frequency, we found the same pattern here, but hands in 3D and feet in 2D drops a little bit. For exertion, we found that the feet method led to more exertion, and especially in 3D. And for fatigue, the same pattern was found. So for the qualitative feedback, we found that participants rated the head and the hands method roughly similar. So they preferred these two methods roughly similar compared to the feet method. We also found that participants really found the hand methods to be the most realistic, as it was akin to rowing with oars or paddling. So we also found that while there was no significant difference in VR sickness scores based on SSQ, most participants preferred using the hands method in terms of least sickness inducing. And in alignment with the questionnaire data on exertion and fatigue, most participants perceived feet as the most tiring methods. So comment from participants indicated that the head-based exertion stemmed more from faster rowing, while feet-based exertion stemmed more from mental load. What did we learn by doing this user study? Well, first off, use your head. So when implementing rowing-based exergames in which maneuverability during high velocity is important, head-based steering is likely the most suited method. And steering by rotating your head in the desired direction was the easiest and most intuitive method. But what about exercise? So the purpose of an exergame is also physical activity, and therefore you might ask, which method contributed most to this? Well, we could see that head, hands, and 2D, you could go with higher velocity in this, so you could exert yourself more. But another interesting aspect of this is that going in lower speed is associated with focusing more on muscle endurance instead. So it could depend a little bit on what types of exertion you would like to get for it. And in that case, feet-based method might be more suitable. Most importantly, maybe, is the question, what do you actually prefer? And here we found that the hands are equal to head, so there was no difference there in what we found. This could potentially be explained by the increased sense of realism and enjoyment. And this has also been found in other studies in which the head method outperformed in terms of performance a hand-based method, but people still prefer to use hands for direction. So feet was comparable in 2D, but not in 3D. Why could this be? We could think about some reasons for this. So first, it might be that some people prefer to have their settings inverted. So instead of the up-down that we had, they might want to change that around. Secondly, the feet dexterity seems to vary more between people compared to hand dexterity. And lastly, some suggestions here. We would like to add haptic feedback to the sensors, so participants could get more cues on how much pressure they're applying. For VR sickness, we found no difference between the methods. But if we compare to similar VR applications, we can see that our scores were relatively low. So our scores ranged between 16 to 23, and that's compared to, for example, 32.5 for similar applications. And what could this be? Well, we think that by using a rowing machine, you have some self-motion cues while moving forward. And this reduces the mismatch between the visual input and the physical input. However, this would also explain the differences in 2D and 3D that we saw, because we didn't have any motion vection cues in the vertical direction. For future work, it would be interesting to see how the steering methods impacted proper rowing techniques. We would also be interesting to explore other scenarios. So now we had the coin-based tasks. What about searching, exploration, and maybe longer durations also? And lastly, it would be interesting to explore other metaphors. So now we used a virtual rowing boat, but it could theoretically be mapped to anything. Lastly, I will conclude by saying thank you for listening, and please check out the details in our paper.